In this tutorial video, we are going to show briefly the installation and the use of the software MC2 Analyzer. We proceed with the software installation. To proceed, the user is requested to accept the CAEN license agreement. It is possible to select a user-defined folder for the software installation. The default option is reported in the highlighted field. At the end of the installation, the user can read the release notes of the software. Once the installation window is closed, the user can launch the application by clicking over the icon on the desktop or using the Windows Start menu. This choice depends on the user installation settings. When the software is started, the user can customize the interface. You can see that all windows can be set floating or embedded in the main software windows. In the present monitor, we prefer, for example, to have a visualization which allows to control many of the configuration parameters. We now proceed to load an energy spectrum. This can be done through the icon in the toolbar, the pull-down menu file, and the button Add located in the Spectrum List menu. It is possible to load the spectrum offline from file. The user can select the folder containing the file. Otherwise, the user can acquire a spectrum online connecting the analog acquisition channel of the CAEN device. Once the online acquisition is selected, we can proceed with the device connection. We specify the parameter for the connection of the device. We see that in this case we connected the device of the family DT5780, mixed high voltage polarity and serial number 367. To view more detailed information on the board, the user can push the board info button. When the device is added to the list of the connected one, the list of available channels is shown on the graphical interface. To add an online spectrum, the user is required to select the channel corresponding to a checkbox in the Add column. It is possible to start the acquisition using a pre-existing saved spectrum, and it is possible to load a configuration file to set the acquisition settings of the specified channel. We underline that the spectrum file may also contain the channel configuration parameters used in the previous acquisition. In this case, selecting the starting spectrum, the field configuration file acquires the default status, which implies that the acquisition configuration is taken from the previous one. It is always possible to change the configuration parameters later on. In this particular case, we use the default configuration parameters. What happens is that the program loads a void spectrum with the default channel configuration saved in the file. When the spectrum is loaded, the corresponding label appears in the spectrum list. This list allows the user to manage multiple spectra loaded from file or acquired in real time, and it is possible to rename the spectrum. We can now focus our attention on the high voltage channels for the detector bias, and you can see the corresponding panel, called HV channels, used for their configuration. To detect the radiation interaction in the detector, we need to turn the high voltage channel on. The user can set the voltage, the maximum haloed current, and voltage, the slope of the voltage ramp up and ramp down through the HV channels panel. The user can also monitor the voltage and the current real time and select the status of the high voltage. The detector we are going to use needs negative polarity, a bias of 700 voltages with a current below 130 microamps. We set a maximum voltage of 720 volts, a ramp up of 50 volts per second and a ramp down of 50 volts per second. We turn the high voltage channel on and it is possible to observe that voltage and current are rising. When the channel status turned to on, the voltage of the channel has reached the predefined value with the current stably below the maximum level. We now proceed with the configuration of the acquisition channel. At first stage, the user has to observe the digitizer electric pulses of the detector. To do so, the user can activate the program tool called Signal Inspector through the button shown on the toolbar. When that tool is selected, the program pops up a notice. This notice informs that when waveforms are acquired, some dead time can be generated because of high data transfer. This window asks the acknowledgement to proceed and gives the possibility to cancel the option in case the user selected it accidentally. When the inspector is started, the program adds a new tab where the user can observe the detector electric pulses. We start now the acquisition and we observe the acquired data. The user can change the visualized waveforms through the configuration panel of the Signal Inspector. It is possible to choose between different options of digital or analog traces, select the gain, the offset of the digital traces and modify the length of the acquisition window. The configuration of the acquisition parameters can be done using the panel acquisition setup. It can be visualized using the icon in the toolbar, using the option in the pull-down menu called View, otherwise the toolbar in the spectrum list. The acquisition setup window contains two tabs. One related to the parameters of the device, one related to the parameters of the acquisition channels. At first stage, we need to observe the properties of the input signals. We select Input Trace in the Signal Inspector window and push on the button Apply to confirm the selection. In case the user does not want to be required to confirm the selection all times, it can push the button Auto Apply. You can see that all settings are applied automatically. We start modifying the offset of the DC input. The polarity of the signals can be changed, but in this particular case the default option is already correct. In case the polarity is negative, the user is required to change the option. When the user changes one of the parameters, has to push the Apply button to confirm the change. As in the previous case, the Auto Apply button allows the user to not confirm all changes. You can see that the negative polarity option inverts the signal polarity in the Signal Inspector. It is possible to change the DC offset through the scroll bar or directly writing the value in the corresponding field. In our case, we set it to small values around 1000 ADC counts. The user can select the dynamic range of the acquisition channel of the device DT5780. In this case, we select the range of 3.7 volts peak-to-peak. This choice increases the gain of the channel and the signals appear higher on average. In the Trigger tab, it is possible to configure the pulse selection. The user can set a threshold and the pulse rise time, which represents the timescale of the filter RC/CR² used for the selected events. You see that changing this value, the trace RC/CR² in red, changes shape. It is also possible to set the trigger hold-off, which represents the time when the device does not accept new triggers after a valid trigger. The user can visualize the trigger hold-off using the Signal Inspector Configuration tab. You can now observe the length of the trigger hold-off in comparison with the shape of the acquired pulses. The user can zoom in, tracing a rectangular area on the window. The user can also reset the scale by a right-click and selecting the corresponding option in the list. The user can place two cursors in the Signal Inspector window. The red cursor can be moved with a simple left click on the screen. A green cursor can be placed or moved on the plot. The user has to press and hold the button Shift of the keyboard and do a left click with the mouse. These cursors are placed on top of one of the analog traces. To select which of the analog trace, the user has to select one of the checkboxes in the Signal Inspector Configuration tab. The cursors can be useful because the Windows Signal Inspector cursors provides the relative distance between the cursors. When the user has selected the proper configuration of the trigger hold-off and input rise time, it can proceed with the configuration of the trigger threshold. The user can visualize the trigger threshold on the Signal Inspector and set a value of the threshold which is above the noise level. We now proceed with the configuration of the parameters for the energy measurement, done with the trapezoidal digital filter. The user has to set the parameters as trapezoid rise time, flat top and signal decay time. The user has to modify the value of the rise time to find a better system resolution. The decay time has to be set at the value of the preamplifier discharge. It is necessary to cancel the so-called pole zero. Another setting is related to the amplitude of flat top of the trapezoidal filter. This parameter is important because the device algorithms samples the energy value at the top of the trapezoid during the flat top. The user can set the time when the energy measurement is done and visualize it on the Signal Inspector. Moreover, it is possible to configure other parameters: the number of samples averaged to provide the trapezoidal height, the hold-off of the baseline restoration, the hold-off of the trapezoidal peak sampling. This last prevents trapezoidal peak sampling too close in time to a valid sample peak. The settings can be set to be suitable for a higher resolution measurement, a balanced setup, or for a higher rate condition. Another important parameter for the energy measurement is the number of samples used to compute the signal baseline. In this particular case, the baseline has been computed with the information of 16 samples. We increase the number of samples to obtain a more stable and precise baseline value. The effect of the baseline evaluation can be seen applying an improper pole zero cancellation and reducing the number of samples used for the baseline calculation. You can observe on the Signal Inspector that the baseline changes quickly its value. These last settings are not suggested and may cause a degradation of the energy resolution. We have now finished with the configuration of the acquisition. We now stop the signal inspector mode by closing the corresponding window or using the button located in the toolbar. You can see that events have been accumulated in the histogram also during the signal inspector mode. In this case, the changes we have done on the acquisition parameters have generated a useless spectrum. We can now stop the acquisition, reset the spectrum, and start a new acquisition. The window properties shows important information, useful to monitor the acquisition or understand the properties of an offline spectrum. The user can select the criterion used to stop the acquisition. The user can find the pull-down menu in the spectrum list to stop the acquisition manually, after a defined lifetime, after a defined real time, or after a defined number of acquired events. We now set a limit on the acquisition lifetime of 300 seconds. In this way, the spectrum is filled until the lifetime is below 300 seconds, and this criterion is applied only on the channel we selected. We now start the acquisition and we apply the spectrum autoscale on the toolbar to better observe the spectrum. The user can enlarge the horizontal axis, having the cursors as reference. It can use the button in the toolbar or the button plus on the keyboard. The user can zoom out using the button in the toolbar or the button minus on the keyboard. It is also possible to enable or disable the autoscale of the vertical axis with the corresponding button on the toolbar, and it is possible to zoom in, tracing a rectangular area in the plot. The user can scale the spectrum on the horizontal axis to contain the full spectrum or reset the visualization to the default configuration. The user can define some regions of interest, called ROI, through the option reported in the ROI editor window. To create a new ROI, we push the button Add, then we can write the starting and ending values expressed in ADC counts. Otherwise, we can set the ROI boundaries on the plot with a left click to start and another left click to stop. The user has to press button Done to confirm the ROI edited. When the ROI is created, its area in the histogram is highlighted by a different color, which can be changed in the pop-up window. The program shows in the histogram the estimated background. When the user selects the ROI with the left button, the corresponding entry is highlighted in the ROI editor window and the Gaussian fit is drawn on the histogram. The user can define several regions of interest. All the selected ROI are listed in the ROI editor window. When one of the entries is selected, the corresponding ROI is pointed by the vertical pointer. All the ROI properties are reported in the Properties window. The user can use two different fitting methods, which are selectable through the pull-down menu tools. The available methods are simple or advanced. In the first, a Gaussian is traced with the average and sigma deviation calculated from the histogram distribution. In the second, a Gaussian fit is obtained from a chi-square minimization. You can see qualitatively how the results of the two fitting methods are slightly different. The user can also choose the algorithms to estimate the background. There is a simple option and an advanced one. The first algorithm evaluates the background with a linear interpolation, while the second uses an iterative method which we are going to illustrate. Now the acquisition is stopped since the lifetime reached the maximum set. The parameters to be set for the advanced background estimation are collected in a window. It is accessible through the pull-down menu Tools, then the option Configure in the section Background. The low-level discriminator represents the first point used for the estimation of the background. The first value should not be above the energy threshold selected by the trigger. A low value can cause a wrong background estimation. The high-level discriminator sets the last point used for the background estimation. The last parameter is the number of iterations of the algorithm. The user should select the proper value. A low number of iterations can overestimate the background, while a high number of iterations gives a smooth background distribution, which tends to underestimate the background content. The user can calibrate the spectrum through the Calibration Setup window. It can be opened through the button in the toolbar. Whenever the user tries to calibrate the spectrum without providing the proper configuration, the program opens automatically the Calibration Setup window. The calibration requires the user to provide a few points in terms of ADC counts and energy, expressed in keV or in MEV. When the user does a left-click on the histogram, the value of corresponding ADC channel is reported in the energy calibration window. If a region of interest is selected, it is possible to obtain the centroid position with high accuracy. Then we write the energy value corresponding to the measured photo peak and add the calibration point to the list. When at least 2 points are added, the program shows the value of the parameters of a linear fit. With 2 points, a linear fit is available, but if more points are added, higher-order polynomials can be used. When the calibration is applied to the spectrum, the centroid positions are expressed in keV. Moreover, other properties of the region of interest are expressed in keV. In this case, the peak corresponding to 1.173 keV has a full width half maximum of 31 keV. It is possible to visualize the spectrum in a logarithmic scale, to better observe small peaks as the sum peak on the right side. It is possible to define a region of interest around the sum peak and use the value of its centroid to have another data point for the spectrum calibration. In this case, we can select a linear interpolation, which uses a chi-square minimization or a quadratic interpolation. It is possible to add more data points, and the program will calculate automatically the interpolated curve. To remove a region of interest, the user can press the button in the Region of Interest Editor toolbar. The user can set the total number of channels of the spectrum. In this case, the spectrum is composed of about 16,000 channels, and we are now reducing them to a total of about 4,000 ones. You can observe that with the spectrum rescale, the calibration values are automatically rescaled. The user is required to apply the calibration to the new spectrum. In any case, the configuration of the background is not changing, so it is necessary to modify the number of iterations for its estimate. While the low-level and the high-level discriminators are modified automatically, the number of iterations are not. The choice of the histogram channels is connected to the number of events collected and the resolution required. In this case, the granularity of the plot is reduced significantly by the change of the channel number. If the user closes the program MC2 Analyzer while the spectrum online is still active, the data is not lost. The user has to launch the program again, connect the same board and activate the same channel. The default settings are taken from the last acquisition done before the program was closed. The spectrum is loaded, preserving the statistics and the region of interest. The user can then start a new data taking, starting from the previous spectrum. The user can connect additional devices specifying different connection parameters and add more acquisition channels. In this case, you can see that we added a new channel and a new entry is shown in the spectrum list. By a click on the spectrum, the user can select which spectrum has to be active. You can see that now we have the previous spectrum on about 4,000 channels and the new spectrum of about 16,000 channels. We can rename the spectrum. We now use a splitter to acquire the signals from the detector using two channels. It is possible to copy the configuration parameters of the first channel to the second one. This can be done with the function export. The user has to select the channel configuration to be copied and save it to file. The user can load the configuration parameters through the import command and select the channel which has to be configured. We can now see that the parameters of the two channels are the same. In case there were too many spectra loaded, the user can hide or show the spectra in the histogram window. When there are two channels enabled in the same device, it is possible to use the request of coincident events. You can access the Coincidence Configuration tab through the Board tab. In this case, we configure channel 0 to acquire events when there is a coincidence of events in the channel 0 and 1. It is possible to set the logic requirement through the pull-down menu, and we select the option AND. The user can set the coincidence window, which is common for all channels. We now configure channel 1 in OR condition with itself. In this way, channel 1 will trigger independently, while channel 0 will trigger when coincident events are registered into the two available channels. We now start the acquisition and see that both spectra are acquiring events. When we scale the spectrum of the channel 1 to the same value of channel 0, we can see that the spectra are similar and are acquiring events at the same rate. We now disconnect the cable of channel 0 and see that the events are acquired only by channel 1. If we invert the situation, we can see that both channels are not acquiring events, since channel 0 is requested to be in coincidence with the other channel. We now reconnect both channels and configure channel 1 to trigger in case there is an anti-coincidence of events. We can now observe that channel 0 is triggering, while channel 1 is not, because the anti-coincidence never occurs. We now disconnect channel 0 and we can see that channel 1 is the only one to acquire evens. We stop the acquisition and reset both histograms at the same time by clicking on the R button in the spectrum list window. We have now finished our demonstration and switch off the high voltage channel. We press the switch in the high voltage channel window and wait that the voltage is down. We then close the program.